Okay, so we have finally come to the definition of Galois group of a polynomial. So let's start with this definition. Let the splitting field of this polynomial f over the field capital F be K. Okay, so small f is a polynomial over capital F and K is its splitting field, which means that K is the extension of f having smallest possible degree, but at the same time K contains all the roots of f. Then this group with which we are now very familiar is actually called the Galois group of the polynomial fx. Now this group can also be considered as a group of permutations of the roots of fx. That's because for any root alpha of fx, you take any sigma from this group of automorphisms, apply that on alpha, that is also going to be a root of fx. That's why. And now we come to the final result of this section, the fundamental theorem of Galois theorem. So that is the focus of this video. Let's now go through that theorem. It is theorem 566. So the beginning of this theorem is just like this definition. Let fx be a polynomial over capital F, K be its splitting field and G, K, F be its Galois group. There is actually no need to write this last part because that is known. In such a situation, this is called the Galois group of fx. But now we see we are going to set up an association between objects coming from two sets. For any subfield P of K containing F, let us consider the set G, K, T. So T is any subfield of K, but as F as a subfield of its own, it contains F. G, K, T is the set of all automorphisms sigma coming from G, K, F, which fix all the elements of T. So this G, K, T is just like the original Galois group, G, K, F, such that T sigma is equal to T for all T belonging to T. So for a subfield T of K containing F, we are getting a group of automorphisms. That is, you can see that by definition that is going to be a subgroup of the Galois group. For a subfield of K, we are getting a subgroup of the Galois group. Now in the other direction, and for any subgroup H of the Galois group, let KH be the set of those X in K such that X sigma is equal to X for all sigma belonging to H. So that means this is nothing but the fixed field of the group H. In the other direction, a subgroup of the Galois group is giving us a subfield of K containing F. This association between subfields of K containing F and subgroups of the Galois group is going to give us a one-to-one correspondence between these two sets of T with this group sets up a one-to-one correspondence from the set of all subfields of K containing T and the subgroups of the set of all subgroups of the Galois group. Containing F, sorry, I think I said containing T, containing F and oh no, the way we are writing this, let's have a one-to-one correspondence from this set onto the set of all subgroups of the Galois group such that some things happen. A number of statements are going to be made now which are true. Five statements. That correspondence enjoys these properties. Number one, the subfield T turns out to be equal to the fixed field of the group G, K, T. Okay, so that is one thing. The second one is that the subgroup H turns out to be equal to the group G of automorphisms of K relative to the fixed field of H, that is KH. Then number three states that the degree of K over T is equal to the order of the group of automorphisms of K relative to T. And there is one more claim here. The degree of T over F is equal to the order of the Galois group divided by the order of the group G, K, T. In other words, this part 3 says that the degree of K over T is equal to the order of the group G, K, T. And the degree of T over F is the index of that group in the Galois group. The number 4 is a normality criterion. This number 4 is very beautiful. T is a normal extension of F. I mean, T of course is an extension of F because it contains F as a subfield. Now it is going to be normal if and only if the group G, K, T is a normal subgroup of the Galois group. Normal extension corresponds to normality of subgroup. Is that why it's called normal extension? I don't really exactly know the reason for calling such extensions normal. This is a normal subgroup of the Galois group. And the fifth one says something when T is normal. If T is a normal extension of F, then see, if T is a normal extension of F, then obviously this is a normal subgroup of this by part 4. So you can consider the quotient of the Galois group by this normal subgroup. Now that quotient becomes isomorphic to the group G, T, F. Okay, so now we are going to prove this. But before we see the proof, let us see what the association is, because we have, the statement is so long, no? So let us see in a kind of figure what this association actually is. This is the set, let me just give it a name, okay? A is the set of subfields of K containing F, and B is the set of subgroups of the Galois group. And the correspondence we are talking about takes T in this set. So T is a subfield of K containing F and gives us this subgroup of the Galois group. Let us give this correspondence the name psi. So actually psi is a mapping, okay, it's a function. We are claiming that psi is a one-to-one correspondence and these properties are true. So now let's see the proof. The proof starts with a statement that we have seen why that statement is true in the proof of the previous theorem. And the first statement is this: since K is the splitting field of Fx over capital F. By this last part, over capital F, we mean when we consider Fx as a polynomial over F, then K is the splitting field of Fx. So it is also the splitting field. It is means K. When K is also the splitting field of Fx over T. Over T means, you see, if Fx has all its coefficients coming from capital F, then since T contains F, those coefficients in particular are also in T, and that is why we can consider Fx a polynomial over T as well. And in that case also K is the splitting field of Fx. Why this is true? We have seen, you go back to the previous field theory video. There, while proving theorem 565, we made sense of this, why this is true. Okay, so this is true. But then by that theorem itself, I think, no? Yeah. So by theorem 565, K is a normal extension of T. What does that theorem say? This theorem says that K is a normal extension of a base field if and only if K is the splitting field of some polynomial over that base field. So here K is the splitting field of fx over T, so that is why K is a normal extension of T by that theorem. Hence, okay, so now what can we say about the fixed field of this group? The fixed field of the group G, K, T. The notation for that is this K suffix G, K, T. Because K is a normal extension of T, by the very definition of normality, this fixed field is just T. And this is part 1. Part 1 asks this. Okay. Now we see what we have to do in part 2. In part 2, we have that subgroup capital H. So part 2 starts by considering the fact that K is a normal extension of F also. In fact, for that we need not write all these things. Already it is given that K is the splitting field of small fx over F. So again by theorem 565, that itself tells us that K is a normal extension of F. So we can just simply write this. Since K is a normal extension of F, in brackets you can of course write if you want, by theorem 565 again. So then what can we say? So we are now going to recall another result that we have already seen. Theorem 564. So by theorem 564, the subgroup H is equal to G of K, KH. You go back to the statement of this theorem. We have two parts there. One part says just this. Okay, so from there itself directly we have this. And so that actually shows part 2. But now using this part 1 and part 2, we can say that our function psi is actually a one-to-one correspondence. It's a bijection. Also, this implies that psi is 1, 2. You see, in the text you won't find any name psi like this given to that association, that one-to-one correspondence. So if you do not use names, you will have to write many things. That's why I named the function psi, the set of subfields of K containing F, capital A, and the set of subgroups of the Galois group, capital B. So now you can simply write that psi is onto. But why is it onto? How exactly are we concluding that it is onto? this is A, this is B. So this is psi. We have taken what? H, any subgroup of our Hilbert group. That means this is any element in capital B. What we have shown is that this is G of K comma KH. So by the definition of psi, we have KH here, the fixed field of the group H. And by the definition of psi, the psi image of KH is actually equal to this. Here we have simply used the definition of psi, but that is nothing but H. And that is why psi is onto, because of part 2. But now we will use part 1 to prove that psi is 1 to 1 as well. It's also injective. For that, let T1 and T2 be two elements in A. This means that they are subfields of K, both containing F, such that their psi images are equal. Our aim is to now show that they are equal. Then, by the definition of psi, G, K, T1 is equal to G, K, T2. But then, by part 1, T1 is equal to K, G, K, T1. But if these two groups are equal, their fixed fields would also be equal. And again, by part 1, this is nothing but T2. So we have proved that if images are equal, then inputs are also equal. Thus, psi is 1 to 1. So being 1 to 1 and onto, we have proved that psi is a 1 to 1 correspondence between the sets A and B. Now here we have used half of theorem 564. To prove part 3, we are now going to recall the other half. So part 3 starts like this. Since K is a normal extension of T. How that is true, we have already seen while proving part 1. By theorem 564, again, okay, this time instead of having this, we are going to concentrate on the degree of K over T. Degree of K over T is equal to the order of the group of automorphisms of K relative to T. And this is happening because K is a normal extension of T. In general, we know that if K is a finite extension of T, then this degree is greater than or equal to the order of the group. Whether we have or don't have normality, we have that inequality. But normality implies equality. So that's what we get from 564 also, besides having this. But then, so this I think is one half of the claim of part 3. But then we also have something else. But then the degree of T over F is equal to the degree of K over F divided by the degree of K over T. this is the order of the Galois group, and this just now we have shown is the order of this group. So that's how the degree of T over F is the index of this group in the Galois group. Okay, so that fully, everything of part 3 has now been proved. Next, part 4. Oh, we did not actually put the numbers, no? We are just simply doing this in different paragraphs. Now, part 4 claims that T is a normal extension of F if and only if this is a normal subgroup of the Galois group. To prove this, we are going to start with a condition which may seem like something out of the blue. Suddenly, without rhyme or reason, we are considering something, but that is going to give us something useful. So the condition is this: let T sigma be contained in T. T sigma is the image of T, image of the field under the automorphism sigma, for all sigma belonging to the Galois group. Suppose we consider this condition, then what are we going to get? Now, because we are working with fields of characteristic 0, so every finite extension is a simple extension. So T is going to be a simple extension of F, and that is by theorem 551. Okay. By theorem 551, T is equal to Fa. T is obtained by adjoining any a suitable single element to F for some A belonging to K. Fields of characteristic 0 are very nice, but those of finite characteristic, I don't want to say nice, but they behave in a manner that is normal to us. But fields of finite characteristic behave so different from what we expect. But that is why they are interesting also. So here you have simple extension. So now you go back to the proof of theorem 565. That means the result we proved in the previous video. There, at one point of the proof, we did this. Let me just first write the thing and then you will understand. Now, but before that there is one more line. Now note that A is an element of T, of course. So we have A sigma belonging to T for all sigma in the Galois group. Why? Because A is in T, so because of this containment relation, if you apply any sigma on A, that is again going to be in T. And now we are going to say, so as we saw in the proof of theorem 565, T is the splitting field of the polynomial, this polynomial Px equal to product of linear factors of this for A sigma as sigma varies over the Galois group. See, the Galois group is going to be finite. So this product is well defined. I mean, there is no question of having or not having convergence. Those things are not there. It's a finite product. This polynomial over f. This fact also we saw while proving this theorem, that ultimately if you multiply out the terms, you then get elementary symmetric functions in the A sigmas, and it turns out that they ultimately actually belong to F. Okay. So this is something we have already seen, and now we are going to use it. So by theorem 565, I think I am running out of ink. Just give me a moment. So theorem 565 is going to give us what? It gives us normality of an extension. Here we are seeing that T is the splitting field of a polynomial over F. So T now is going to be a normal extension of F. T is a normal extension of F. That is the conclusion. So what have we got here? The condition that T sigma is a subset of T for every sigma coming from the Galois group. That condition has implied that T is a normal extension of F. But now we are going to show that the converse is also true. Conversely, let T be a normal extension of F. So if we are able to prove that the converse is also true, then T being a normal extension of F will be equivalent to that condition. So we can then work with that condition. Okay. Again, by theorem 551, T is equal to Fa for some A belonging to K. You may be thinking, why I am writing this again? That's because this is one part. Okay, we are now doing something afresh. Afresh means we are doing something entirely different. So we need to again write it. Alright, now the minimal polynomial of A over F has all its roots in T. The minimal polynomial Px, let us call it Px of A over F has all its roots in capital T, because T is a normal extension of F, by Again, theorem 565. But we also know something else, that the Galois group is a group of permutations of the roots of the polynomial. Now, A sigma is a root of Px for every sigma belonging to the Galois group. Alright. So, what sigma you are going to apply on A, it does not matter. Whatever you are going to get, that is again going to be a root of Px. And what does that mean? It means that, wait, something is not okay. I think did I make a mistake? Let me just see. Something is not okay. Oh no, okay. There is no problem. I mistook something. There is no problem in our proof. Whatever we have written is correct. So, A sigma belongs to T for all sigma belonging to the Galois group. Where is this coming from? That is because we have just now said that Px has all its roots in T, and we are also saying that A sigma is a root of Px for every sigma in the Galois group. So all these roots are going to be in T. So on A, whatever automorphism we apply from the Galois group, that is going to land us in T. Since T is equal to Fa, this implies what? Because T is ultimately Fa, so any element in T is going to be an expression which is a rational function in A. The numerator will be a polynomial in A with coefficients from F, and the denominator also will be like that. So, applying sigma on A does not get us outside of T, it keeps us inside T itself. And of course, applying sigma on F is going to be inconsequential, nothing is going to change. So, the conclusion we can draw from this is this, that applying sigma on any element of T ultimately is going to keep us inside T itself. That's why T sigma is contained in T. That is why not only is this condition giving us that T is a normal extension of F, but the converse is also true. So, we can write T is a normal extension of F if and only if T sigma is a subset of T for all sigma belonging to the Galois group. So now instead of working with this normality, we can now work with this to show that this condition itself is equivalent to normality of that subgroup in the Galois group. So now we aim for that. Now a consequence of this is this. So T is a normal extension of f if and only if for any sigma belonging to the Galois group, any tau belonging to the group G, K, T, and any T belonging to T, we are going to get this. Should we apply tau first or sigma? No, sigma first. Sigma first and then tau. That is going to give us this again. Why though? Why is it the case? You see, normality of T over F is equivalent to having this thing, right? So now if we choose any sigma from G, K, F, when you apply that sigma on this arbitrary element of T, this T sigma will be where? Again in T. On that, if you apply any such tau, it's not going to change. Why? Because tau by definition does not change anything of T. So we get this. Another way of writing this is this, i.e. T sigma tau sigma inverse is equal to T. If you apply sigma inverse on both sides, you get this. But then, this means this last condition, this is equivalent to what? You see, so sigma tau sigma inverse is giving us what? It does not change any element of T, which means what? It belongs to, let me show it here, sigma tau sigma inverse is then an automorphism of K that is fixed on T. Fixed on T means identity on T. So it has to belong to this G, K, T. So we have chosen any element sigma from here, and tau is any element from here. And we have got this, which means that if you consider this conjugate of this group given by sigma, then this is going to be contained in G, K, T. So we can write sigma G, K, T sigma inverse is a subset of G, K, T. But then G, K, T is normal in the Galois group. And this is in turn equivalent to the statement that G, K, T is normal in the Galois group. And that is why T is a normal extension of F if and only if G, K, T is a normal subgroup of the Galois group. So this is part 4. And now finally part 5. In part 5 it is given that T is a normal extension of F. So let T be a normal extension of F. Okay, now we are going to choose an arbitrary element from the Galois group. Let sigma be any element in G, K, F. Since, so we have already seen while proving this part 4 that P sigma is going to be contained in T. We have this now, and this coming from the fact that P is a normal extension of F. Since we have this, the mapping sigma star from T to T given by T sigma star is equal to T sigma is an automorphism of T. You see, we are able to have this map because sigma maps T into T. In other words, T is invariant under sigma, so we have been able to restrict the domain of sigma from the original K to T, and the second set, which some people call codomain, some call range, that thing also we can take as T. And because it's simply a restriction, so this is going to again be an automorphism, but this time of T. Moreover, sigma star leaves F fixed since sigma does so. That is because sigma star is nothing but rule wise, after all it's just sigma, and sigma fixes every element of F because it's coming from the Galois group. So sigma star also fixes every element of F. In other words, sigma star is an automorphism of T which fixes all the elements of F. Hence, sigma star belongs to the group G, P, F. Moreover, for any sigma and psi belonging to, the author has called this mapping psi. However, we already have a psi, no? Our original one-to-one correspondence. So let me just give it some other name. Let me, what can I call it? Suppose mu. Okay. And also for any sigma and mu belonging to the Galois group, one can verify, I mean it's just a simple matter to verify this, that sigma mu star is equal to sigma star mu star. So the mapping theta from the Galois group into this group sigma t comma f given by sigma theta equal to sigma star is a group homomorphism. Because we have fields also, no? So in order to avoid any confusion, I am calling it a group homomorphism because it's the map between groups preserving structure. Now we need to see what its kernel is. Let sigma belong to k theta, the kernel of theta, which means what? Then sigma star is equal to sigma theta is going to be the identity in this group, and that identity is just the identity map on T. So it's just the identity map on T. But then what? What does that mean? It means that when we apply sigma on the elements of T, capital T, nothing changes. And that is why sigma has to belong to this group G, K, comma 2, because originally sigma is an automorphism of K, but now it leaves capital T fixed. Hence, the kernel of theta is contained in this group G, K, comma T. K theta is a standard notation in this book for group kernels, okay? I mean group homomorphism kernels. But the converse is also true. Conversely, how that is true, I am leaving to you to realize. Conversely, also, I mean, it's just a matter of seeing why this is true. You do not even have to do anything. It's almost clear, immediately clear. Thus, the kernel is equal to this. But we are not in a position to immediately apply the first isomorphism theorem for groups because we don't yet know whether theta is onto or not. For that, we can, however, apply the first isomorphism theorem and instead write this. So, the image of the Galois group under theta is isomorphic to the quotient group of the Galois group by that group, this group. Okay, this is an application of the first isomorphism theorem. Now, so this isomorphism tells us that the order of this image is equal to the order of this G, K, comma F, the order of the Galois group divided by the order of this group. However, this thing is equal to the index of T over, the degree of T over F, and this is by part 3, and this degree is nothing but the order of the group this, and this is coming from theorem 564. So we see that our function theta is actually onto, because this image, which in general is a subgroup of this, has the same order as that group. Hence, theta is onto. Thus, the group G T, F is isomorphic to the quotient group of the Galois group GK, F by the group GK, T. And that's what we wanted to prove in this fifth part. So that's it. That is the proof of the fundamental theorem of Galois theory. And with this section ends. So next the exercises will start. But for today the video ends here itself. So that's just it for tonight. See you in the next upload. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.